Hello, all. Can you hear me? Hello, guys. Can you hear me? Okay. So today we will solve some questions on EM and Gaussian mixture models. Right. So even before going to the problem sheet, I'll quickly walk over this EM. Um, so feel free to stop me if you guys don't get any point. I'm sharing the screen. Yeah, so you can see the screen, right? Okay. So basically, EM is an expectation maximization algorithm. So why do we use this algorithm is right. So we want to find the maximum likelihood of basically maximum likelihood estimate of the distribution, right? You are given the samples. What you observe is excess and you assume some distribution p that is parameterized by theta, I mean, right, and you try to maximize this theta, maximize this probability of uh, observing x by varying theta, right? That's why it is maximum likelihood uh, estimate, right? So why do we use em is used when directly optimizing p of x given theta is difficult, when especially when you have the knowledge that there is some uh, hidden variables inside it, right? You don't directly observe those hidden variables, but it's the process. There is a process that is happening. Let's say some z1, you are seeing some x1, right? Again, z2 is causing x2. So what you are seeing is x1s and x2s, not z1s and z2s, right? So under such cases, right, when you want to estimate the uh, probabilities distribution, right? So you use the m, right? This is a maximum likelihood estimate algorithm, right? So yeah, quickly I'll walk over this thing, right? So what you maximize is maximize p of x is same as maximizing log p of x. Okay, so we can assume that we are observing samples x1, x2, x3, and so on, right? So, and these are independent samples, right? So this thing will become a summation, right? This will be log of p of xi theta. Okay, so now, right, so because there are some hidden variables inside you, which and you don't know, you don't have any information about them, right? So what you do is you write this, you expand this thing, right? You just do sigma z log of, sorry, there is, right, sigma I, can say zi here, p of xi zi, and assume this is parameterized by some theta, right? And summing over zi p of xi zi is nothing but p of xi theta, right? So now this, when you try to differentiate with respect to theta, right, this becomes untractable. So right, so you have come up with some approximate algorithm, come up with an approximate algorithm to maximize this quantity, sorry, uh, so what you do is, uh, basically idea is you have something like this, right? And you want to maximize this function. So what you do is, at every, when you are here, right, you try to create some lower bound about this, and you try to maximize this thing, and you reach here, right? You create a lower bound and try to maximize each time. Yeah, so that's the basic main idea, right? So towards that, yeah, this is a trick. What you have to do is just multiply and divide by some probability distribution, q of z. You don't know about this, but you have to estimate this, right? So now this is nothing but what, this is summation over I, your log, and this can be written as an expectation of this quantity, right? Since q is a probability distribution, you can think of this as an expectation of this, right? P of xi zi parameterized by theta divided by q of zi. Okay, so this is it, right? So an expectation is taken with respect to this distribution q, and right, so now we want a lower bound on this thing, right? So there is something called as Jensen's inequality, right? So what it says is, you have expectation of f of x, if f is convex, right, this thing holds. F is convex. If it is concave, right, the reverse holds. F of E of x. If it is concave, right, I'm representing concave by like this, right? Convex is something like this for shorthand. So now your E is this thing and put F as log and X is this quantity, right? So you develop an upper bound by using this Jensen's inequality on this. So we are continuing from this point. After this, we are continuing this point, right? What you get here is this is greater than expectation of Q times your log of this thing P of xi zi divided by Q of zi. All right, right. So what happens is if you take this quantity and subtract from this thing, right, what you get is um, so basically what you can write this as exactly this is equal to your expectation of Q log of this thing done by Q of zi plus what should I put it, expectation underscore Q log of Q of zi by P of zi given x. Okay, yeah, so this is what we want to get. So you got this expression by subtracting this from this, and this quantity is always positive, right? So that's why this is greater than this, as you have seen this. Okay, so this is now what you do is you iteratively find, because you don't know Q and you don't know theta, both you have to estimate in EM, right? So you find Q, you initialize some theta, you start with some theta, and you find Q. How do you find Q? You set Q to this guy. Q of Zi is nothing but P of Zi un x, right? You set, you initially set theta, then find Q by setting Q to this, right? So by setting Q to this, what happens is you try to meet this guy, log P, at any point x, right? And then once you have Q set to this thing, right, then you use this Q in this and substitute in this expression and then maximize this thing. Now next step is this theta maximum. This is an expectation step, E step, and this is M step. As here you maximize this thing, E of Q right? So once you have this theta, right, again you try to uh, set the with that theta, get this thing, and get q of zi. Again, once you get q of zi and substitute this, and then try to um, find theta, right? So this thing will fail, this algorithm will fail if this is not tractable, right? If you cannot, if this thing p of z given xi is not tractable, right, em will not work. In this setting, em will not work if this is not tractable. Okay, so how do we relate this to Gaussian mixture models is, so here we have, you observe some data, right? You observe some data x1, x2, and so on, x and so on, and you know that it is coming from the mixture of Gaussians, right? Let's say you know that. Now you want to find out the exact distribution of underlying distribution of this thing, right? Now here, what are the things you need, right? You need mean, mu, and you need variance of each Gaussian, and you need what is the probability of occurrence of each Gaussian, and that is pi. Like for multi-dimensions, this can be a covariance matrix, and this is mean. This will be a vector, and this will be a matrix, and this is a probability distribution over the Gaussians. Okay, so this is a quick overview of your EM algorithm. Right. So, any questions on this thing? I will start solving questions quickly. Right. Yeah. So this is it. What are the necessary conditions for this to be a density function? So you want p of xn to be a valid density. So what are the necessary conditions? Right. So any responses? Right. So yeah, for this to be valid density, right, all your the pi's are probabilities, and your sigma pi should be one, right? So that is one thing. Yeah. In this question, right, so you are given these are nothing but contour plots and the density map, let's say, of the data, and you are asked to estimate how many clusters are there, how many Gaussians are present in this density. You just need to see the figure and gauge the answer, right? So here we see, like, the one cluster, I mean one Gaussian, there is another Gaussian here, and here also there is one more Gaussian, and here it is one more Gaussian. Right, so in total we have four, right? So Now, in the same question, what is the minimum value of k prime that is not equal to k for which we get a similar density estimation? I mean, in this question, what 4 is the ideal answer. If not 4, what is the minimum k that fits this data? B, it's a minimum. I'm saying it is not equal to 4. When it is not equal to 4, what is the best you can do? Answer is 2. No, 2 is not the answer. It is 3. So you can have one Gaussian fit here and one Gaussian fit here, and there's two for this two. This is one more Gaussian. I mean, well, if I mean it, well, it is two. You can consider two also, but um, yeah, I mean, if it is specified, let's say if you are given some more constraint, let's say your error has to be within something, right? Then yeah, you just have to choose the next best thing from 4. And yeah, now the question is, assume equal pies for each Gaussian after convergence, right? So convergence here relates to that algorithm whatever I was talking there, right? You find q, you find theta, you keep repeating it, and once it settles down, right? What should be the pies for the models you get with k prime in q3? Yeah, so pies are nothing initially. Let's you I mean, from the figure it's clear that your pies for 4 clusters each will be equally likely, so you get 1/4. And when you merge these two clusters, right, so their prior probabilities will also get merged, right? So that is nothing but yeah, 0.25, 0.25, 0.25, 0.25, you will have it. But once you are done merging those two clusters, your probabilities will also add up. So that is 0.5, and that is C. So yeah, now you are given this orange points, right? So um, and you try to fit a Gaussian mixture model on this orange points. Right, what you see is the data, right? And you try to fit a Gaussian mixture model on that. So why do you think that fit is not good? I think that's the first question, right? Yeah. What is the problem with this? Any questions? B. Right. So the clusters are not sampled from Gaussian, right? So if the clusters have been sampled from Gaussian, you would have seen a blob, a circular blob, and your fit would have been appropriate. So yeah, what can be done to mitigate this problem? So what you can do is, you can increase the number of Gaussians. So yeah, so this GMM has the power to represent complicated distributions with when you allow the number of Gaussians to increase, right? And yeah, so that's the thing, right? You can increase the value of k to allow the model to fit to a larger number of Gaussians to approximate nearly non-Gaussian distributions, right? So with the k is equal to 8, you got this thing. Remember, this is not a Gaussian, one Gaussian. This counter you are able to see by introducing 8 Gaussians, right? And the overall, this is what it has fitted onto the overall data, right? This is something, wherever orange is not there, that's what it has estimated uh, on that point. um, yeah, so what does soft clustering mean in GMMs? Any ideas? D. So let me spend some little time on this thing. So in the last week we discussed KNNs, right? So what we have got is some data points, and we have three clusters, and we want to cluster this thing. I mean, this data can be in pretty high dimensions also. Yeah, but because it is three, you are able to visualize. But yeah, you want algorithm to do this, not you visualizing things, right? So no, because for this, just for the sake of it, let's say I have initialized three clusters with centers mu1, mu2, and mu3. So how will I assign a point to my cluster? In sorry, it's not k nearest neighbors. K means, sorry, that's my mistake. K means clustering, right? So let's say you have x1, x4, x5, x7. And what I mean is, let's say you have data x1, x2, x3, x4, x5, and so on. So what you do is you find the distance of all the points from this point mu1, right? So whichever is minimum, uh, sorry, from x1 you find distances to this mu1, mu2, and mu3. Whichever is closer to x1, that guy is assigned to mu1, right? And similarly for x2, right? You find distance from x2 and mu2 and mu3, and whichever is closer you uh, assign it to mu1, mu2, mu3. Say you have mu1 and mu2 and mu3. So here mu1 will contain x1. Once x1 is assigned to mu1, it will not contain, it cannot be assigned to mu2 again, right? So that's let's say you have got this thing, and x2, x5, x6, and x7. So this is a hard assignment of the data points to the clusters. You either belong to this cluster or you don't belong to this cluster. That's it, right? In probabilistic assignment of clusters, right? What you do is your point x1 doesn't belong to just mu1, mu2, or mu3, right? It say it belongs to mu1 with say probability point 0.8, belongs to this thing with probability point 0.2, and belong so point 0.1, right? So point 0.3, right? So you don't take hard decisions in the soft clustering, right? Which is nothing but the Gaussian mixture models, right? So that's the crucial difference between your k-means and the g-mems. Yeah, GMMs does soft clustering and K-means does hard clustering. Soft clustering. Okay, so yeah, this is what I wanted to highlight regarding the K-means and uh, why it is hard clustering and why this is soft clustering. Right. So yeah, that brings that samples are assigned probabilities of belonging to a particular cluster. Right. So that's what soft clustering. And yeah. Yeah, so what is the update for PyK uh, in the EM algorithm for GMM, right? So yeah, this should be simple if you refer to your lecture, right? Um, so that's a standard uh, question regarding this GMM. And what else? Yeah, KNN is a special case of GMM with the following properties. Any question responses? B and D. Yeah, so I think that's all I have for today. Focusing mostly on the GMMs and its relation to K-means clustering. If you guys have any queries or questions, um, you can ask me. I'll try to answer. Uh, I think there is one more thing pending. The learning theory part, probably that. I think there is last. Next week will be the last week for tutorials. Um, right. So I think there is something related to some statistical learning. Probably in the last. Maybe next week we will discuss that. And yeah, apart from that, I think it should be over. I guess by now. Exam practice? No, I am not aware. But and sometime back, as you guys discussed, did you guys get a hold of any questions so that we can solve? Okay. Which algorithm of clustering do you recommend when you have a lot of categorical variables and only few numeric? Um, I mean, directly, if you use any uh, it's algorithms such as k-means and all, right? Um, I mean, you need to uh, bring it into the scale of this numerical feature of numerical variable. Right? Otherwise they don't make sense. So I mean, bottom line, what I want to tell is you need some kind of pre-processing before using any clustering algorithm for this kind of uh, mixed data, right? And that pre-processing depends upon the domain knowledge of that. I mean, suppose numerical variable doesn't carry much significance, right? You just want to not use it in the first place. And same holds for the categorical variables. I mean, not dummy variables. So let's say uh, let's say you have some examples like some variable takes a, let's say a, b, c, and d. Right now, depending upon the domain knowledge, if giving, if whenever it takes value a, right, and your output is responding to that a, right, so output is more for a, and for b it is less, right? So assigning some real numbers along that trend makes sense. So that's what I meant. And I mean, this is for not for clustering. I mean, in for any classification or regression problem. And the safest way to do that is, let's say you have A, B, C, D, four features, right? Just convert it to one hot, and then normalize your features. So that should take care in practice. Not dummy variables. Dummy variables, I mean, doesn't make sense. Categorical variables comes in many forms, right? So somebody, that's what I said. So the class of tickets, right? Tickets belongs to class A. Class A means high price. So if you want to um, find a person if he is wealthy or not, let's say for a weird classification problem, right? Then this class is very much correlated to that output, right? So yeah, so that's what, there's no hard and there's no rule of thumb that I can give you, right? So depending upon the task at hand, you have to do it. So these things you will encounter as you try to solve problems. So there is a website called Kaggle, right? There you can try to solve some problems. So you will definitely end up having categorical features which are useful and how to deal with them. And typically algorithms such as random forests, decision tree based algorithms does a good job of handling the categorical and both this thing, the real numerical features. But coming to clustering, yeah, I don't have a clear answer unless you have any domain knowledge of the data. So yeah, if you guys don't have any more questions, we can stop, or I can answer if you guys have questions. No, I am not aware what is rule-based clustering. So yeah, I think you guys can focus on questions such as for neural networks per se, why ReLU activations are good, why not sigmoid? Guys have any answers for that? So for neural networks, we use non-linearity, right, after every layer. So there are different non-linearities. You have tanh, you have ReLU, and you have sigmoid. So which activation is better? No, no, no. That's not the right answer. Um, I mean, for what you want to have is, first of all, it should capture non-linearity, and it should be easy to compute, right? And it should not cause your uh, you know gradients to vanish. So these three things are important. So out of these, sigmoid and tan h and ReLU, right? So ReLU is typically preferred for the reasons that I just mentioned. Yeah, so that there are many resources on this. You can just have a read on those things, right? It's useful to know these things. mm, and you can say, why don't you use regression loss, mean squared error, for classification problems, right? So these questions can, you should know, you guys should know these kind of questions, right? Okay, guys. So we can meet next week if you guys don't have any more questions.